Today we're taking on one of the most important building blocks of probability and risk management: random variables. If probability tells us how likely an event is, random variables let us translate those events into numbers we can actually work with. And once we have numbers, we can measure, model, and manage risk. What is a random variable? A random variable is a rule that assigns a number to every possible outcome of an experiment. In risk management, this is how we capture uncertainty. If a bond defaults, we record it as 1. If it survives, we record it as 0. If we track daily returns, the variable might take any real number between -infinity and +infinity. That simple mapping from uncertain outcomes to numbers is what allows us to build risk models. Discrete versus continuous. Random variables. Random variables come in two types: discrete and continuous. A discrete random variable has a countable set of outcomes. Examples: rolling a die, outcomes 1 through 6. A Bernoulli trial, only 0 or 1. Number of defaults in a credit portfolio, 0, 1, 2, and so on. A continuous random variable has uncountably many outcomes within an interval. Examples: stock returns, interest rates, loss severity in insurance claims. Why does this matter? Because the tools we use, PMFs or PDFs, depend on whether the variable is discrete or continuous. Probability mass function and distribution functions. For discrete variables, we use the probability mass function PMF. It tells us the probability of each possible value. Example: in a Bernoulli random variable with parameter p, the probability of getting 1 is p, and the probability of getting 0 is 1 minus p. To complement this, we use the cumulative distribution function CDF. This gives us the probability that the random variable is less than or equal to some value. For a Bernoulli, the CDF is a step function: 0 until 0, then it jumps to 1 minus p, and finally jumps to 1 at 1. Key takeaway: PMF gives probabilities at points. CDF accumulates probabilities up to a point. And importantly, the CDF fully characterizes the distribution of a random variable. Expectations. The workhorse of risk management. The expectation of a random variable is its weighted average outcome. Formally, E of x equals the sum of x times its probability for all possible x. This is where probability meets finance, because expected value is central to pricing, valuation, and capital modeling. Expectations also extend beyond raw variables. We can take the expectation of any function of x. For example, the expected payoff of an option depends on the distribution of the underlying price through a nonlinear payoff function. One critical property: linearity of expectation. The expectation of a times x plus b times y equals a times e of x plus b times e of y. This is why portfolio expected return is just the weighted sum of expected returns. Moments. Describing risk beyond the mean. Moments summarize the distribution of a random variable. 1. First moment: mean, the central tendency. Second moment: variance. Spread around the mean. Standard deviation, its square root, is in the same units as the mean. Third moment: skewness. Measures asymmetry. Negative skew signals downside risk, a common feature of equity and credit returns. Fourth moment: kurtosis. Measures tail fatness. High kurtosis means more extreme events than the normal distribution predicts. Why should risk managers care? Because relying on just the mean and variance blinds you to skewness and fat tails. Many financial crises came from ignoring skew and kurtosis. Jensen's inequality. Convexity in action. Here's a concept with real-world bite. Jensen's inequality says that for convex functions, the expectation of the function is greater than the function of the expectation. In risk terms, this explains why options and other convex payoffs have value even when the expected underlying move is zero. Volatility creates positive expected payoff for convex instruments. Transformations of random variables. Risk managers constantly rescale and shift variables. For example, converting raw returns into percentages, normalizing data to compare across markets. Linear transformations behave predictably. Means shift with the constant term. Variance scales with the square of the rescaling factor. Skewness and kurtosis remain unchanged under positive scaling because they're dimensionless. This lets us safely transform variables without losing key risk properties. Quantiles and robust measures. Not all distributions behave nicely. Heavy tails can make means and variances misleading or even undefined. That's where quantiles come in. The quantile function, the inverse of the CDF, maps probabilities to outcomes. Two critical measures. Median, the 50th percentile, splitting probability mass in half. Interquartile range, the spread between the 25th and 75th percentiles. These are robust alternatives to the mean and variance, much less sensitive to extreme tail events. This is why regulators and practitioners often prefer quantile-based risk measures like value at risk. Continuous random variables and PDFs. For continuous variables, the PMF is replaced by the probability density function, PDF. Important points. A PDF itself is not a probability. Probabilities come from integrating the PDF over an interval. The total area under the PDF is 1. The most familiar continuous distribution is the normal. Its bell-shaped PDF is fully described by its mean and variance. But remember, real-world financial data often show heavier tails and skewness than the normal allows. Why random variables matter in risk management. Let's connect the dots. Random variables convert uncertainty into measurable quantities. Distributions describe how likely different outcomes are. Expectations and moments let us summarize and model those outcomes. Quantiles provide robust alternatives when tails dominate. PDFs and CDFs give us the machinery to calculate probabilities in both discrete and continuous worlds. Every tool in modern risk management, from value at risk and expected shortfall to credit portfolio models and stress tests, rests on this foundation. Closing random variables are not just theory. They are the language we use to describe, model, and act on risk. If you understand probability mass functions, cumulative distribution functions, expectations, moments, quantiles, and transformations, you hold the keys to interpreting market behavior, pricing risk, and building resilient portfolios. This is why mastering random variables isn't optional for risk managers. It's essential.